Good morning, good evening, जिथे जो greeting accept करियो and page number 228 problems with classical theory. How do we know that classical physics is not actually true of our world? The main reasons are experimental. Quantum theory was not wished upon us by theorists. It was with great reluctance that they found themselves driven to the strange and in many ways philosophically unsatisfying view of a word. Yet classical theory, despite its superb grandeur, has itself some profound difficulties. The root cause of this is that two kinds of physical objects must coexist. Particles, each described by a small finite number of parameters, and fields requiring an infinite number of parameters. This dichotomy is not really physically consistent. For a system with both particles and fields to be in equilibrium, all energy gets taken from the particles and put into the fields. This is a result of the phenomenon called equipartition of energy. At equilibrium, the energy is spread evenly among all the degrees of freedom of the system. Since the fields have infinitely many degrees of freedom, the pure particles get left with none at all. In particular, classical atoms would not be stable, all motion of the particles getting transferred into the wave modes of the fields. Recall the solar system picture of the atom as introduced by the great New Zealand British experimental physicist Ernest Rutherford in 1911. In place of the planets would be the orbiting electrons, and instead of the Sun, the central nucleus on a tiny scale held by electromagnetism rather than gravity. A fundamental and seemingly insurmountable problem is that as an orbiting electron circles the nucleus, it should, in accordance with Maxwell equations, emit electromagnetic waves of an intensity increasing rapidly to infinity in a tiny fraction of a second as it spirals inwards and plunges into nucleus. However, nothing this is observed. Indeed, what is observed is quite inexplicable on the basis of classical theory. Atoms can emit electromagnetic waves, but only in bursts of very specific, discrete frequencies, the sharp spectral lines that are observed. Moreover, these frequencies satisfy crazy rules which have no basis from the point of view of classical theory. Another manifestation of the instability of the coexistence of the fields and particles is the phenomenon known as black body radiation. Imagine an object at some definite temperature, electromagnetic radiation being in equilibrium with particles. In 1900, Rayleigh and Jeans had calculated that all the energy would be sucked up by the field without limit. There is a physical absurdity involved in this, and nature herself more prudently. And at the low frequencies of field oscillation, the energy is as Rayleigh and Jeans had predicted, but at the high end, where they had predicted catastrophe, actual observation showed that this distribution of energy does not increase without limit, but instead falls off to zero as the frequency increases. The greatest value of the energy occurs at a very specific frequency for a given temperature, that is color. The next topic is the beginning of quantum theory. How are these puzzles to be resolved? The original Newtonian scheme of particles certainly needs to be supplemented by Maxwell's field. Can one go to the other extreme and assume that everything is a field, particles being little finite sized nodes of some kind of field? This has its difficulties also for them. Particles could vary their shapes continuously, wriggling and oscillating in infinitely many different kinds of ways. But this is not what is seen. In the physical world, all particles of the same species appear to be identical. Any two electrons, for example, are just the same as each other. Even atoms or molecules can take on only discretely different arrangements. If particles are fields, then some new ingredient is needed to enable fields to take on discrete characteristics. In 1900, the brilliant but conservative and cautious German physicist Max Planck proposed a revolutionary idea for suppressing the high frequency blackbody modes, that electromagnetic oscillations occur only in quanta. Whole energy E bears a definite relation to the frequency V given by E is equal to h of V, h being the new fundamental constant of nature, now known as Planck's constant. Astonishingly, with this outrageous ingredient, Planck was able to get theoretical agreement with the observed dependence of intensity with frequency, now called the Planck radiation law. Planck's constant is very tiny by everyday standards. With this bold stroke, Planck revealed the first glimmerings of the quantum theory to come, although it received scant attention until Einstein made another astonishing proposal that the electromagnetic field can exist only in such discrete units. Recall that Maxwell and Hertz had shown that light consists of oscillations of electromagnetic fields. Thus, according to Einstein, and as Newton had insisted over 2 centuries earlier, light itself must, after all, actually be particles. How is that light can consist of particles and of field oscillations at the same time? These two conceptions seem irrevocably opposed, yet some experimental facts clearly indicated that light is particles and others that it is waves. In 1923, the French aristocrat and insightful physicist Prince Louis de Broglie took this particle wave confusion a stage further when, in his doctoral dissertation for which approval was sought from Einstein, he proposed that the very particles of matter should sometimes behave as waves. D. Broglie's wave frequency V for any particle of mass m again satisfies the Planck relation combined with the Einstein E is equal to mc squared. This tells us that V is related to m by hv is equal to E m is equal to mc squared. Thus, according to de Broglie proposal, the dichotomy between particles and fields that had been a feature of classical theory is not respected by nature. Indeed, anything, whatever which oscillates with some frequency v can occur only in discrete units of mass hv by c square. Somehow, nature contrives to build a consistent world in which particle and field oscillations are at the same thing. Or rather, her word consists of some more subtle ingredient, the word particle and wave conveying but partially appropriate pictures. The Planck relation was put to another brilliant use by Niels Bohr, the Danish physicist and towering figure of 20th century scientific thought. Bohr's rule required that the angular momentum of electrons in orbit about the nucleus can occur only in integer multiples of h by 2 pi, for which Dirac later introduced the convenient symbol h with a strike through is equal to h over 2 pi. Thus, the only allowed values of angular momentum about only any one axis are 0, h naught, 2, h naught, 3, h naught, 3, 4, h naught. With this new ingredient, the solar system model for atom now gave to a considerably accuracy many of the discrete stable energy levels and crazy rules for spectrum frequencies that nature actually obeys. Though strikingly successful, Bohr's brilliant proposal provided a somewhat provisional patchwork scheme referred to as old quantum theory. Quantum theory, as we know it today, arose out of two independent later schemes which were initiated by a pair of remarkable physicists, a German Vernon Heisenberg and an Austrian Erwin Schrödinger. At first, their two schemes, matrix mechanics in 1925 and wave mechanics in 1926, respectively, seemed quite different, but they were soon shown to be equivalent and subsumed into a more comprehensive and general framework, primarily by the great British theoretical physicist Paul Adrian Murray Dirac soon afterwards. In the succeeding sections, we shall be catching a glimpse of this theory and of its extraordinary implications. The famous two-slit experiment is the next topic. Let us consider an archetypical quantum mechanical experiment according to which a beam of electrons or light or some other species of particles is fired through a pair of narrow slits to a screen behind. To be specific, let us take light and refer to the light quanta as photons in accordance with the usual terminology. The most evident manifestation of the light as particles occurs at the screen. The light arrives there in discrete, localized units of energy, this energy being invariably related to the light's frequency in accordance with Planck's formula E is equal to hv. Never is the energy of just half a photon received. Light reception is an all or nothing phenomena in photon units. Only whole numbers of photons are ever seen. They have a picture of two slit experiment with monochromatic light. However, a wave-like behavior seems to arise as the photons pass through the slits. Suppose first that only one slit is open, the other being blocked off. After passing through, the light will spread out by the phenomena called diffraction, a feature of wave propagation. But one may still hold to a particle picture and imagine that there is some influence exerted by the proximity of the edges of the slit which causes the photons to be deflected by some random amount to one side or another. When there is a reasonable intensity to the light passing through the slit, that is a large number of photons, then the illumination of the screen is seen to be very uniform. But if the light intensity is cut right down, then one can ascertain that the distribution of illumination is indeed made up of individual spots in agreement with the particle picture. Where the individual photons strike the screen, the smooth appearance of illumination is statistical effect due to the very large number of photons involved. For comparison, a 60-watt light bulb emits about 1 and it has 15 or 20 photons per second. Photons indeed appear to be deflected in some random way as they pass through the slit, with different probabilities for different angles of deflection, yielding the observed distribution of illumination. However, the key problem for the particle picture comes when we open the other slit. Suppose that the light is from a yellow sodium lamp, so that it is essentially of a pure unmixed color. The technical term is monochromatic. That is, one define the wavelength of one defined wavelength or frequency, which in the particle picture means that the photons will have the same energy as the wavelength is about 5 into 10 raised to power minus 7 m per millimeter. Take the slits to be about 0.001 millimeter in width and about 0.15 millimeter apart, the screen being about 1 meter distance. For a reasonably strong light intensity, we still get a regular looking pattern of illumination, but now there is a waviness to it, called an interference pattern, with bands on the screen without 3 millimeters in width near the center of the screen. We might have expected that by opening the second slit we would simply double the intensity of illumination on the screen. Indeed, this is true if we consider the total overall illumination, but now the detailed pattern of intensity is seen to be completely different from what it was with the single slit. At some points on the screen where the pattern is at its brightest, the intensity of the illumination is 4 times what it was before, not just twice. At others, where the pattern is darks, the intensity goes down to zero. The points of zero intensity perhaps present the greatest puzzle for the particle pictures. These were points where a photon could quite happily arrive when just one of the slits was open. Now that we have opened the other, it suddenly turned out that the photon is somehow prevented from doing what it could do before. How can it be that by allowing the photon an alternative route, we have actually stopped it from traversing either route? On the scale of the photon, if we take its wavelength as a measure of its size, the second slit is some 300 photon sizes away from the first. So, how can the photon know when it passes through one of the slits whether or not the other slit is actually open? In fact, in principle, there is no limit to the distance that the two slits can be from one another for this cancelling or enhancing phenomenon to occur. The slits from the photon's point of view, how can it make any difference to it whether the second slit some three? As the light passes through the slit, it now seems to be behaving like a wave and not like a particle. Such cancellation, destructive interference, is familiar as a property of ordinary waves. If each of the two routes can be traveled separately by a wave, and if both are made available to it, then it is quite possible for them to cancel to one another out. In picture 6.7.1, I have illustrated how this comes out. When a portion of the wave coming through one of the slits meets the portion coming through the other, they will reinforce each other if they are in phase. That is to say, when the crests of two portions occur together and the troughs occur together, but they will cancel each other out if they are exactly out of phase. With the two slit experiment, the bright places on the screen occur whenever the distance of two slits differ by an integer number of wavelengths, so that the crest and troughs do indeed occur together, and the dark places occur when the difference between the two distances come exactly midway between these values, so that crest meets the trough and trough with crest. With purely wave picture, we can understand the pattern of bright and dark bands that the screen, although not at the discreteness in terms of interference of waves. There is nothing puzzling about an ordinary macroscopic classical wave traveling through two slits at once in this way. A wave, after all, is just a disturbance, either of some continuous medium or some substance composed of myriads of tiny point like particles. A disturbance could pass partly through one slit and partly through another, but here things are very different. Each individual photon behaves like a wave entirely on its own. In some sense, each particle travels through both slits at once and it interferes with itself. For by cutting the overall intensity of light down sufficiently, one can ensure that not more than one photon at a time is passing the vicinity of the slits. The phenomena of destructive interference, whereby two alternative routes for the photons somehow contrive to cancel one another out as realized possibilities, is something that applies to single photons. If one of the two routes is alone open to the photon, then the photon can travel that route. If the other route is alone open, then the photon can travel that route instead. But if both are open to it, then the two possibilities miraculously cancel one another out, and the photon appears to be able to travel neither. The reader should pause to consider the import of this extraordinary fact. It is really not that light sometimes behaves as particles and sometimes as waves. It is that each individual particle behaves in a wave-like way entirely on its own, and different alternative possibilities open to a particle can sometimes cancel one another out. Does this photon actually split in two and travel partly through one slit and partly through the other? Most physicists would object to this way of phrasing things. They would insist that while the two routes open to the particle must both contribute to the final effect, these are just alternative routes, and the particle should not be thought of as splitting into two in order to get through the slits. As support for the view that particle does not partly go through one slit and partly through the other, the modified situation may be considered in which a particle retractor is placed at one of its slits or the other, since when it is observed a photon or any other particle always appear as a single whole and not as some fraction of a whole. It must be the case that our detector detects either a whole photon or no photon at all. However, when a detector is present at one of the slits, so that an observer can tell which slit the photon went through, the wavy interference pattern at the screens disappears. In order for the interference to take place, there must apparently be a lack of knowledge as to which slit the particle actually went through. To get interference, the alternatives must both contribute, sometimes adding, reinforcing one another by an amount which is double what one might expect, and sometimes subtracting so that alternatives can mysteriously cancel one another out. In fact, according to the rules of quantum mechanics, what is happening is even more mysterious than that. Alternatives can indeed add the brightest point on the screen, and alternatives can indeed subtract the dark points. but they must actually also be able to combine together in other strange combinations, such as alternative of a plus I into alternative of b, where I is the square root of minus 1 that we encountered in chapter 3. In fact, any complex number can play such a role in combining alternatives. The reader may recall my warning in chapter 3 that complex numbers are absolutely fundamental to the structure of quantum mechanics. These numbers are not just mathematical niceties, they force themselves on the attention of physicists through persuasive and unexpected experimental facts. To understand quantum mechanics, we must come to terms with the complex number weighting. Let us consider what these entail. Next topic is probability amplitudes. There is nothing special about using photons in the above description. Electrons or any other kind of particle or even whole atoms would do equally well. The rules of quantum mechanics appear even to insist that cricket balls and elephants are to behave in this odd way, where different alternative possibilities can somehow add up in complex number combinations. However, we never actually see cricket balls or elephants superposed in this strange way. Why do we not? This is a difficult and even a controversial issue, and I do not want to confront it just yet. For the moment, as a working rule, let us simply suppose that there are two different possible levels of physical description, which we call the quantum level and the classical level. We shall only use these strange complex number combinations at the quantum level. Cricket balls and elephants are classical level objects. The quantum level is the level of molecules, atoms, subatomic particles, etc. It is normally thought of as being a level of very small scale phenomena, but this smallness does not actually refer to physical size. We shall be seeing that quantum effects can occur over distances of many meters or even light years. It would be a little closer to the mark to think of something as being the quantum level if it involves only very tiny differences of energy. I shall try to be more precise later, especially in chapter 8. The classical level is the macroscopic level of which we are more directly aware. It is the level at which our ordinary picture of things happening holds true and where we can use our ordinary ideas of probability. We shall be seeing that the complex numbers that we must use at the quantum level are closely related to classical probabilities. They are not really the same, but to come to terms with these complex numbers, it will be helpful first to remind ourselves how classical probabilities behave. Consider a classical situation which is uncertain, so that we do not know which of two alternatives A or B takes place. Such a situation could be described as a weighted combination of these alternatives, P into alternative of A plus Q into alternative of B, where P is the probability of A happening and Q is the probability of B happening. Recall that the probability is the real number lying between 0 and 1. Probability 1 means certain to happen, and probability 0 means certain not to happen. Probability half means equally likely to happen as not. If A and B are only alternatives, then the sum of these two probabilities must be 1. That is, P plus Q is equal to 1. However, if there are further alternatives, this sum could be less than 1. Then the ratio P ratio Q gives the ratio of the probability of A happening to that of B happening. The actual probability of A and B happening out of just these two alternatives would be P over P plus Q and Q over P plus Q respectively. We could also use such an interpretation if P plus Q is greater than 1. This might be useful, for example, whenever we have an experimental that is performed many times, P being the number of A occurrences and Q number of B occurrences. We shall say P and Q are normalized if P plus Q is equal to 1, so that they give the actual probabilities rather than just the ratio of probabilities. In quantum physics, we shall do something that appears to be very similar to this, except the P and Q are now the complex numbers, which I shall prefer to denote instead by W and Z respectively. W of alternative A plus Z of alternative B. How are we to interpret W and Z? They are certainly not ordinary probabilities, since each can independently be negative or complex, but they do behave in many ways like probabilities. They are referred to as probability amplitudes and simply amplitudes. Moreover, one often uses the kind of terminology that is suggested by probabilities, such as there is an amplitude W for A to happen and an amplitude Z for B to happen. They are not actually probabilities, but for the moment we shall try to pretend that they are, or rather, the quantum level analogies of probabilities. How do ordinary probabilities work? It will be helpful if you can think of a microscopic object, say a ball, being stuck through one of two holes to a screen behind, like the two-slit experimenter described above. But where now is a classical macroscopic ball replaces the photon of the previous discussion, there will be some probability p of st that the ball reaches the top hole t after it struck it s at some probability p s of b that it reaches the bottom hole b. Moreover, if we select a particular point P on the screen, there will be some probability Pt of P that whenever the ball does pass through T, it will reach that particular point P on the screen, and some probability PBP that whenever it passes through B, it will reach P if only the top hole is T is open. Then to get probability that the ball actually reaches P via T after it is struck, we multiply the probabilities that it gets from S to T by the probability that it gets from T to P. Similarly, only the bottom hole is open, then the probability that the ball gets from S to P is PS or P to PVP. If both holes are open, then the probability is then it gets from S to P, where still is first expression PS of T into P of T is just as only T were open, and the probability that it gets from S to P via B is still P, S to B, and PBP. So the total probability P of SP that reaches is becomes the sum of the equations we just derived. At the quantum level, the rules are just the same, except that now it is these strange complex amplitudes that must play the roles of probabilities that we had before. Thus, in two-slit experimental considered above, we have an amplitude A of st for a photon to reach the top slit T from the source S, and an amplitude of A of Tp for it to reach point P on the screen from the slit T, and we multiply these to get the amplitude for it to reach the screen P via T. As with probabilities, this is the correct amplitude assuming that the top slit is open, whether or not the bottom slit B is open. Similarly, assuming that B is open, there is another amplitude, and for a total amplitude, we just do like we did two probabilities, we add those two amplitudes. This is all very well, but it's not much use to us until we know how to interpret these amplitudes when a quantum effect is magnified until it reaches the classical level. We might, for example, have a photon detector or a photon cell placed at P, which provides a way of magnifying an event at the quantum level, the arrival of photon at P, into a classical discernible occurrence. Say an audible click. If the screen acts as a photographical plate that the photon leaves a visible spot, then this would be just as good. But for clarity, let's stick to use a photocell. There must be an actual probability for the click to happen, but not just one of these mysterious amplitudes. How are we to pass from amplitudes to probabilities when we go over from the quantum to the classical level? It turns out that there is a very beautiful but mysterious rule for this. The rule is that we must take the squared modules of the quantum complex amplitude to get the classical probability. What is a squared modulus? Recall our description of complex numbers in an argand plane. The modules z of a complex number z is simply the distance from the origin of the point described by z. The squared modules is simply the square of this number. Thus, if z is equal to x plus y square, the square number modules will be z square is equal to x square plus y square. Note that for this to be an actual normalized probability, the value of z square must lie somewhere between 0 and 1. This means that for a properly normalized amplitude, the point z in the argand plane must then lie somewhere in the unit circle. Sometimes, however, we shall find we want to consider combinations w into alternative b plus g into alternative of b, where v and z are merely proportional to the probability amplitudes, and then they need not to lie in this circle. The condition that they can be normalized and therefore provide actual probability amplitudes is that their squared moduli should sum to unity. W square plus d square is equal to 1. If they are not so normalized, then the actual amplitudes for A and B respectively are this, which do lie in the unit circle. We now see that a probability amplitude is not really like a probability after all, but rather more like a complex square root of a probability. How does this affect things when effects at the quantum level get magnified so as to reach the classical level? Recall that in manipulating probabilities and amplitudes, we sometimes needed to multiply them and we sometimes needed to add them. The first point to note is that the operation of multiplication poses no problem in our passing from the quantum to the classical rules. This is because of the remarkable mathematical fact that the squared modules of the product of two complex numbers is equal to the product of their individual square moduli. This property follows at once from the geometrical description of the product of a pair of complex numbers as given in chapter 3, but in terms of real and imaginary parts, it is pretty little miracle. Try it. This fact has the implication that if there is only one single route open to a particle, that is, when there is only a single slit open in the two slit experimental, then one can argue classically and the probabilities come out the same whether or not an additional detection the particle is made at the intermediate point. We can take the squared module at both stages or only at the end, and the answer comes out the same each way for the resulting probability. However, if there is more than one route available, then we need to form a sum, and it is here that the characteristic features of the quantum mechanics begin to emerge. When we born when we form the squared modules of sum w plus g of two complex numbers w and g, we do not usually get the sum of their squared moduli separately. There is an additional correction term theta. Theta is the angle in which the pair of photons Z and V subtend at the region in the argand plane. It is the correction term 2wz cos theta that provides the quantum interference between quantum mechanical alternatives. The value of cos theta can range between negative 1 and 1. When theta is equal to 0, we have cos theta is equal to 1, and the two alternatives reinforce one another so that the total probability is greater than the sum of the individual probabilities. Geometry picture: when the theta is equal to 180, we have a cos theta is equal to negative 1, and the two alternatives tend to cancel one another out, giving the total probability less than the sum of the individual one destructive interference. When theta is equal to 90, we have a cos theta is equal to 0, and we get an intermediate situation where two probabilities do add. For a large and complicated system, the correction terms generally average out because the average values of cos theta is 0, and we are left with the ordinary rules of classical probability. But at the quantum level, these terms are give important interference effects. Consider the two-slit experiment. When both slits are open, the amplitude for the photon to reach P is the sum W plus G, where here W is this and G is this. At the brightest point on the screen, we have a W is equal to Z, so cos theta is equal to 1. Hence, W plus G square is equal to V square is equal to 4V square, which is 4 times the probability of W square for when just the top slit is open, and therefore 4 times the intensity when there is a large number of photons. In agreement with observation at the dark points in the screen, we have W is equal to negative of Z, so that cos theta is equal to negative 1. Hence, this there is zero destructive interference. Again, in agreement with observation at the exactly intermediate points, we have W is equal to Iz or W is equal to negative Iz, so that the cos theta is equal to 0, hence giving you twice the intensity for just one slit. We shall see at the end of the next section how to calculate where the bright, dark, and intermediate places actually are. One final point should be remarked upon: when both slits are open, the amplitude for the particle to reach P via T is indeed W is equal to A of amplitude of S via T and into amplitude of T via P, but we cannot interpret in squared modules, that is square modules of W square, as the probability that the particle actually passed through the top slit to reach P. That would give us nonsensical answers, particularly if P is at the dark place on the screen. But if We choose to detect the photon's presence at T by magnifying the effect of its presence or absence there to the classical level. Then we can use a module of AST squared for the probability for the photon being actually present at T, but such a detection would then obliterate the wavy pattern. For interference to occur, we must ensure that the passage of the photon through the slit remains at the quantum level, so that the two alternatives route must both contribute and can sometimes cancel one another out. At the quantum level, the individual alternatives routes have only amplitudes, not probabilities. Thank you. That's this topic. Or next topic is the quantum state of a particle, which I will continue